Welcome to section 2.4b. We're going to start this section by talking about the derivative of all 6 basic trig functions. Recall that we have the derivative of sine of x is equal to cosine of x, and the derivative of cosine of x equals negative sine of x. We're going to use this information along with the quotient rule to produce the derivative of the other 4 trig functions: tan x, secant x, cotangent x, and cosecant x. You're going to want to memorize all 6 of these trigonometric functions derivatives, or at the very least understand how we get these derivatives using the basic derivative rules. One thing that you may want to look at first, a problem that students have had in the past, is knowing which one is positive and which one's negative. So the derivative of all of the C functions, the cosine, the cotangent, and the cosecant, are all negative. Now, let's take a look at the derivative of the tangent x equals secant squared x proof. What we want to do first is we want to rewrite the tangent x in terms of sine and cosine. So tangent x is equal to sine of x over the cosine of x. Now if I want to differentiate this, I've got to use the quotient rule. So quotient rule says low times the derivative of the high minus high d low, so minus sine x times the derivative of cosine of x, which is negative sine of x, over low low, so cosine x quantity squared. Now if we clean this up a little bit, we have the cosine squared x, cosine x times cosine x is cosine squared, negative sine of x times negative sine of x, negative times negative is positive, sine of x times itself is sine squared x, or sine of x quantity squared, over cosine x quantity squared. All right, and then we can use a trigonometric identity that 1 equals sine squared x plus cosine squared x to get 1 over the cosine of x squared. 1 over cosine x equals secant x, so 1 over cosine squared will be secant squared. Now let's take a look at the derivative of y equals x minus tan x. Let's start with the derivative of x, which is 1, minus, now we need the derivative of tangent x. If we look up here to our chart, the derivative of tangent x is equal to secant squared x. So I'm just going to drop a secant squared x right in place of the derivative of the tangent x. So the derivative of y equals x minus tan x is 1 minus secant squared x. All right, now let's look at example 5, letter B, where we have y equals x secant x. Well, x is a linear function, secant x is a trigonometric function, so we have to use a product rule in order to find the derivative of y. So y prime is first times the derivative of the second plus the second times the derivative of the first. And then we look in our chart, and you see that the derivative of secant x is secant x tangent x, right, plus secant x times the derivative of x is 1. So there's your derivative. All right, example 6 has y equals in 2 separate forms. All right, so what we're going to do is look at the derivative of each of these forms. They are equivalent, but your final answers can look really different from each other. So in this first form, we have 1 minus cosine x over sine of x, And that's going to require us to use the quotient rule. So y prime is low d high sine of x times the derivative of 1 minus cosine x. The derivative of cosine x is negative sine, so negative sign gives us a positive sign. Right, minus high d low, so 1 minus cosine x times the derivative of sine of x, which is cosine x, over low, so sine squared x. Now, if we choose to clean this up, we're going to have the sine of x squared, or the sine squared x. Then I have to distribute this cosine out along with this negative here. So this gives me cosine x times 1 is cosine x minus, so minus cosine x. And then cosine x times cosine x is cosine squared. Minus times a minus is a plus. And just like in our proof earlier, where sine of x plus sine squared x plus cosine squared x equals 1, we can rewrite this as 1 minus cosine x over the sine squared x. Right, and if we choose to separate it into two parts using the Hart problem, we end up with 1 divided by sine of x is the cosecant x minus cosine x over sine of x is the cotangent x. Now let's differentiate this second variation of y. So y prime equals the derivative of cosecant x is negative cosecant x cotangent x minus the derivative of cotangent is cosecant squared x. All right, I've realized that I made a mistake on this left side over here when I copied from this step to this step. I didn't put my sine squared. All right, so that's going to change my final answer here, but it doesn't change the process that I took to get there. All right, now let's go back and continue this right side derivative and clean it up, and we'll see that it actually does equal this left side over here. All right, let's take a look at number 6, where we have y equals 1 minus cosine. All right, let's take a look at example 6, where I have y equals 1 minus cosine x over sine of x, which if I do my Hart problem, and all right, let's take a look at example number 6. Y equals 1 minus cosine x over sine of x, and y equals cosecant x minus cotangent x. These are the same function, just rewritten using our Hart problem rule, where 1 over sine x equals cosecant x, and cosine over sine of x equals cotangent x. But we're just going to look at the two different differentiation techniques here. All right, so if let's look at this left side. If I want y prime, I've got to use the quotient rule. So I do low times the derivative of the high minus high d low, so minus 1 minus cosine x times the derivative of the sine of x over low, so sine x quantity squared. Right? So the derivative of 1 minus cosine x, the derivative of 1 is 0. The derivative of cosine x is negative sine x, but I already have a negative here. So negative is going to give me a positive. So sine of x times 0 plus the sine of x. Now, it's not necessary to put that 0, but I'm just trying to emphasize all the parts of the derivative rule. All right, now we have minus high D lows, so 1 minus cosine x times the derivative of sine of x is cosine x over low. I'm going to rewrite the sine of x quantity squared as a sine squared x. All right, I could go through and clean this up, but for purposes of finding the derivative, I have found that derivative. So let's look at the right side and the differentiation technique of using the known information from this chart here. All right, so the derivative of cosine x is negative cosecant x cotangent x minus the derivative of the cotangent x, which is the cosecant squared x negative. Right, remember the derivative of all the C trig functions are negative. Right, so we have y prime equals this left one, and then this y prime equals, right, these two are equivalent, but they look very different. But both of them are acceptable. Now we're going to take a look at the trigonometric functions and the chain rule. One of the most important things to do with the trig functions is to make sure you have your parentheses so that you can see the inner functions and the outer functions. All right, so let's look at example 7a, and we're going to take the sine of 2x and we're going to put parentheses around the 2x to let ourselves know that the inner function is 2, is a linear function 2x, and my outer function is a trigonometric function, the sine of blah. All right, so how I want to take the derivative of this is to use the derivative of the outer function. So derivative of sine something is the cosine something, and then times the derivative of that something. Right, so since the inner function is 2x, we multiply by the derivative of that inner function to be 2. Right, on example B, we already have our parentheses. So y prime is the derivative of the outer function, which is the cosine of something function. So the derivative of cosine something is the negative sine something times the derivative of that something. So since the inside is 3x minus 1, we have to multiply by since the inside is 3x minus 1, we have to multiply by the derivative 3. All right, and then on y equals the secant 4x, we put parentheses around the 4x. Now the derivative of secant something is secant something tangent something times the derivative of that something. This is the one that gives students more trouble than the rest. Now in example 8, we want to stay with the routine of putting our parentheses into the problems. So for A, what we're going to do is we want to rewrite it as the sine of 3x raised to the 4th power. All right, but the problem here is that we don't have parentheses around the 3x like we had in the other problem. So when I put that set of parentheses, you can see now that we have an inner function, which is a linear function, 3x. We have a middle function, which is the sine of the 3x. And then we have an outer function, which everything is raised to the 4th power. So what this means is we're going to have to use the chain rule multiple times. Right? with these problems, I typically write out the entire rule. So what I mean by that is I've got something to the fourth power. So the derivative of something to the fourth power is 4 times that something raised to the third power times the derivative of the something. Right? Just like in the other problems, whenever we took the derivative using the power rule, we multiply by the derivative of whatever was inside of the power rule. Well, now we got to take the derivative of the sine of 3x, which is going to require chain rule again. So sometimes these are referred to as chain rules. If there's an inner, middle, and outer function, you have to use a chain rule twice. So our final answer, the derivative, is equal to 4 times sine 3x cubed, that stays the same, times the derivative of sine something. Well, the derivative of sine something is cosine something times the derivative of that something. So here is our final derivative for example 8, part A. Part B, we rewrite it as the secant of x over 2. Actually, I'm going to rewrite the x over 2 as the 1/2 x, and then it's all raised to the 1/2 power. Well, the derivative of something to the 1/2 power using the power rule is 1/2 something to the negative 1/2 times the derivative of the something. Right? Now we bring this part straight down as 1/2 secant 1/2 x to the negative 1/2 times the derivative of secant something is secant something tangent something times the derivative of that something. So here is our derivative of example 8, part B. Now, we could go through and rewrite this and try to clean this up some. We have this 1/2 and this 1/2 here. 1/2 times 1/2 gives us a 4th. All right, so that takes care of that part and that part. All right, secant 1/2 x and tangent 1/2 x like being where they're at. There's no negative exponents, and there's no way to combine that to a single trigonometric function. But this secant 1/2 x to the negative 1/2 x to the negative 1/2 power. The negative 1/2 power tells us that this entire set of parentheses wants to go to the bottom and become a positive 1/2 power. Right? And we know that anything to the 1/2 power, anything to the 1/2 power is the square root of. So we can finish this by rewriting it as the secant 1/2 x tangent 1/2 x divided by 4 on the square root of secant 1/2 x. Now, unless it's a multiple choice question, there's no need to rewrite it from this stage here. Right? So you could have left it as this. And that would be perfectly fine on a free response question. For letter C, we need to rewrite it using some additional parentheses to make it easier for us to see what is the inside, what is the middle, and what is the outer function. So we'll rewrite this as the cotangent of 3 over 2x all raised to the 2/3 power. So my inner function is this 3 halves x. My middle function is the trigonometric cotangent. My outer function is raised to the 2/3. Right, so I'm going to take the derivative of blah to the 2/3 as something to the 2/3 as y prime equals 2/3 something, which is the cotangent 3 halves x, raised to the negative 1/3 times the derivative of the something, which is cotangent 3 halves x. Right, so I'm going to complete the problem by taking the derivative of the cotangent 3 halves x. This first part gets copied down exactly like it is. Nothing else happens to it. And the derivative of cotangent is negative cosecant something, cosecant squared something, so 3 halves x, times the derivative of 3 halves x, which is 3 halves. Alright, so we're going to look at the product and quotient rules that have embedded chain rules. These are the most complicated of the problems, but they're really not too bad as long as you break it apart and look at the different pieces necessary to get your final derivative. Right, and I typically write out all my steps when I'm doing these so that I don't make a mistake. So what I want to do first is I want to rewrite this example 9 as x squared times 1 minus x squared to the 1/2 power. Alright, so the first rule I see is a product rule for the derivative. So I start my derivative by doing first times the derivative of the second plus the second times the derivative of the first. All right, and notice how I have it written as the derivative of here and here rather than trying to do that derivative all in one motion. Once you do several of these problems, that's not too bad to do, but for the first few you want to try to write out as much as possible. Alright, so now y prime equals x squared times the derivative of something to the 1/2. Well, the derivative of something to the 1/2 is 1/2 something to the negative 1/2 times the derivative of that something. So here we had to use the chain rule to make the derivative of 1 minus x squared to the 1/2 plus 1 minus x squared to the 1/2 times the derivative of x squared is 2x. Right, and it is okay to leave it in this form for now. Now, we could rewrite the 1/2 power as the square root of, we could rewrite the negative 1/2 power as 1 over the square root of, and then simplify things like 1/2 of negative 2 and so on. But I'm not going to take the time to do that right now. If this is a free response question, leave this answer. If we want to find the derivative at a point, let's plug in some numbers so we're dealing with numbers rather than the letters. Right, the next example, number 10, we have to use the quotient rule first. So y prime equals low to high. Well, first I'm going to rewrite the low as x squared plus 4 to the 1/3 power. Right, so low to high, x squared plus 4 to the 1/3 times the derivative of x, which we know will end up being 1, minus high to low, so x times the derivative of x squared plus 4 to the 1/3 over low, so x squared plus 4 to the 1/3 all squared. All right, let's do a little cleanup here. x squared plus 4 to the 1/3 times the derivative of x, which is 1, minus x times the derivative of something to the 1/3 is 1/3 something to the negative 2/3 times the derivative of something. Right, divided by the 1/3 squared, well, power to the power where you multiply those, so you get x squared plus 4 to the 2/3. Let's try that again. X squared plus 4 to the 2/3 power. Alright, and our last problem for this section. We have this quotient raised to the second power. So if I'm following order of operations, I've got to use the chain rule first, and then embedded within chain rule is going to be the quotient rule. Alright, so let's start with the derivative of something to the second power is 2 times that something to the first power. So 3x minus 1 over x squared minus plus 3 is inside the parentheses, times the derivative of something. Alright, so derivative of, let's go back over that one more time. The derivative of something to the second power is 2 something to the first times the derivative of that something. Now, in order to take the derivative of the something, we're going to have to use the quotient rule. Alright, so we have 2 times 3x minus 1 over x squared plus 3 times lowdy high x squared plus 3 times the derivative of the top, which is 3, minus high-d low 3x minus 1 times the derivative of x squared plus 3 is 2x over low, so x squared plus 3 squared. And we will circle our answer, f prime of x equals